See, here my research area is FS, so free space optical communication, and up to some extent, I am also working in visible light communication, VLC. So I have made some circuits here in my lab in IIT Jodhpur, uh, and I would like to demonstrate you. I have made a video on that. The circuits that I have made for the VLC visible light communication, I will be demonstrating you in this session. So first we will take some small questions, 3-4 small questions. After that, I will show you the video that I have made on visible light communication. In that video, basically, I am transmitting an audio signal from one place to another place using visual light. So that will be an interesting part. So let's start the question. Then I will show you the video. So you all can answer the questions. First and a very simple question: how many semiconductor layers constitute a pin diode? Yeah, three is the correct answer. Uh, if you can, if you can recall it, the structure of the pin diode is something like this. Here you have P, and this is N. This is the intrinsic layer. Vipul, do you want to say something? Okay. So the structure of the pin diode is something like this. Here, the intrinsic layer is basically a pure semiconductor. The size of the intrinsic layer is quite bigger than P and the N layers. So can anyone tell me why this intrinsic layer is introduced in a pin photodiode? Uh, Although we can have the working with P and N, simple P and N also, but why this intrinsic layer is introduced in between, and what is the working of this intrinsic layer in pin photodiode, or sorry, pin diode? Can anyone?
Sir, because it can generate maximum electron hole pairs.
Yeah, the correct answer. The larger the size of the depletion layers. This is basically uh, introduced. The intrinsic layer is basically introduced to increase the size of the depletion layer, and the larger the depletion layer, larger the depletion layer, and the bigger will be the, or the larger number of electrons hole pair will be generated when a photon is incident on this. So this is the what is the working of pin diode, and this is the reason why our intrinsic layer is capped and why it is a bigger in size as compared to P and N. The next question is related to the noise. The noise due to the random behavior of charge carrier is,
Short noise.
yeah, short noise is the correct answer. And can anyone answer what is the random behavior? Is it the number of random distribution like Gaussian or Poisson or something else?
Poisson process.
Poisson, yeah, correct. So, uh, What is short noise? See, whenever we have a source or a receiver, in that, take it as an EN for understanding. There is a, if it is a source, then there is a generation of photon. If it is a receiver, then there is a generation of electron hole pair. So the charge carriers that are generated in photodiodes are random. The photons that are generated are very random. Photon, see, generation is random. See, the number of photons that are generated or number of electron hole pair that are generated, there doesn't remain fixed. There may be like 10 to the power 16 or 10 to the power something between 10 to the power 20. The number is not a uniform or constant number. So the number keeps on changing. This changing number generate a short noise. Similarly, due to the temperature, there is a thermal noise. Due to the, can anyone tell me what is partition noise? See, partition noise is basically, see, current is flowing like this. If there is any division in current, current needs to divide in between 2 or 3 paths, then there is a partition noise. So this is what is the partition noise, when there is a division of currents in between. So here obviously the random behavior is not due to the partition noise. Partition noise is something different. Next question. Which statement is true for pin diode with respect to APD? You read the option and as per your opinion, you give the answer. A, B, C, or D. Yeah, D is the correct answer. See, we have two kinds of photodiode for the reception of light. One is pin photodiode that we have already seen here. The second is APD, avalanche photodiode. The structure of the avalanche photodiode is somewhat like this. N plus P, pi is the intrinsic layer, and again P plus. The plus is for heavily doped. So this heavily doped regions are created because this heavily doped regions is there. So because of this heavily doped region, the fast moving charge carrier will collide and generate multiple number of charge carriers. See that, like one charge carrier or collide and generate further charge carriers, and then this further charge carrier will collide and create further charge carriers. So there will be an avalanche effect here. So due to this, the charge carriers will be very much, and the amount of current you are getting here will be much higher as compared to the current that you were getting in pin photodiodes. So here we can say that the pin photodiodes, the sensitivity is less. Obviously, sensitivity is less. Sensitivity is high in APT because of this highly doped region, which generate more number of electron hole pairs. The signal to noise ratio is poor as compared to avalanche. Obviously, the current is more. The current that is creating here or that is generating here is high. That's why the SNR will also be improved here. Have good temperature stability. Yes, the temperature stability will be good in photodiode. So all of the above is the correct answer. See, this is a small video I have made in my lab. Here I am transmitting transmitting a light, and I'm transmitting an audio signal using light, and the audio signal is playing through the mobile, and that is transmitted through light. So I'm playing this video. You see, if you have any doubt, we will discuss it after this video. This is a source. No, this is not a source. This is the battery. This is laser. These lenses are to collimate the light so that it moves to longer distance. This is a source. That is the other end of the lab. This is the receiver. To obstruct it, the song stops. So this was the small video that I have made. Do anyone wants to ask anything related to this video?
Which diode was used in this?
We have used a laser here, simple laser. I have purchased that laser from Amazon. It was the cost of the laser was around 2 to 300 rupees. And at the receiver, the solar cells are used. Photodiode, but basically it is a solar cell that again cost around 200 rupees.
And what was the distance?
Distance here I have kept an because we have a limitation in the lab. If you increase the distance, then also it will work, because we are here, you are using a laser. The distance was around I think it was around 15-meter distance was there in lab, from one end of the lab to other end of the lab. It was around 15-meter.
Sir, have we checked the receive level and eye diagram of these particular links?
No, I didn't check the eye diagram of this signal. As of now, I have just transmitted the audio signal and I have listened it.
Okay. What will be the minimum receive level required at the receiver end for a successful transmission?
Receiver means in terms of power you are talking, or
Yes,
in terms of
Power,
what?
sir. Yes, sir. In terms of power, dBm or dB, whatever.
See, I didn't measure the power as it is, but in milliwatt it will work. Means if you send the power in milliwatt, then also it will work.
Okay, okay. Thank you.
So one more thing I want to say, that this works on the principle of intensity modulation. See, this is just a battery. You know why this battery is used, and let me explain in here. This is the circuit diagram of that VLC communication that I have made. Let me explain why that battery is used. So laser or any diode, you know, there is a cut-in voltage of everything. So to rise the level above the cut-in voltage, I have used that battery. Suppose my amplitude of the amplitude of this song that is playing here is like this. Suppose it is like this. So what I am doing, by placing the battery, I am just shifting it up. It shifted somewhat like this. Say this is oscillating between 3.5 to 3 volt. It is oscillating like this, 3.5 to 2 volt. Now at the receiver, what is happening? At the receiver, this is solar cell. What is the receiver? The receiver, see, first the song is played. This is, so the light will glow as per the intensity of the song. If the volume of the song goes high, then light intensity will increase. If the volume of the songs goes low, then the intensity of the light goes low. So the intensity of the light will be according to the volume of the song. And at the receiver, the photo detector again converts. Now, if the intensity of the song increase, then it will accordingly convert the or intensity of the light increase, then it will convert according to the intensity, that the voltage will be converted as per the intensity of the song, and that at the end the speaker will play the song as per the intensity of the voltage that it having receiving by aux cable. So this works on the principle of intensity modulation, which in the lectures like 7th or 8th, sir have also
Hello.
yeah, Vipul, you want to say anything?
Sir, a mobile to LED signal transmit via microphone.
No, via aux cable I have connected.
In form of which is electrical signal.
Yeah, I have
Okay.
directly supplied the electrical signal via aux cable. See, this is mobile to aux cable to one part of the aux cable is given to LED, and
Okay.
LED or laser, you can give anything, either LED or laser, both will work
Okay.
depending upon your application.
Okay.
LED and the other part of the LED was given to false supply. You can keep this resistance or you can omit this resistance. That is up to you.
Okay.
Sir, here that means we are not doing any analog to digital conversion, right?
No.
Because while output is already digital.
Yeah, we are
If
not
I'm
doing
not
any conversion. We are just transmitting the analog signal. It is similar to like amplitude modulation. You have read amplitude modulation in communication, na?
Yes, sir.
So it is similar to that only. It is similar to amplitude modulation only.
Okay. Thank you.
So this is it. Simple project. You can make in your like if you are in BTech or if you want to visualize this thing, you can make by your own also. This is a simple thing, I have also made a relay in this. What I have done, I have taken the output of this solar panel and given it to next LED, and I have transmitted it to a different direction, and that also work. The relay circuit that I have made here, that not only relate the signal but also amplify the signal, relay and amplifying circuit. And I have written a research paper on this part, relay and amplifying circuits, and that is under publication actually. That is under submission. So if that get published, then I will show you that paper also, how I have made a relay, and I will make a video on that, and I will show you once the paper get accepted in the. I have submitted in a conference paper. If it gets accepted, then I will show you that how I have made an relaying and amplifying circuits. Okay, so now this section, now we will be taking some typical numerical type of question here. So you can take out your calculator and all that, and you can start solving along with me here. So here now we will take 3 to 4 numerical type questions. Do anyone of you have any doubt as of till now up to here? Okay. So the question is, the quantum efficiency of a particular silicon APD R is reached through APD is 80% for the detection of an radiation at a wavelength of 0.9 micrometers. When the incident optical power is 0.5 microwatt, the output current from the device after avalanche gain is this much. So you need to determine the multiplication factor of the photodiode under these conditions. So what you need to do? Can anyone answer? First of all, you need to find the photocurrent, that is without multiplication. First of all, you need to find the photocurrent that is without multiplication. Once you find the photocurrent, that is without the multiplication factor, then you can that this is I, this I is with the multiplication factor, that I by IP, you will get the M. So in this question, you need to find the IP. I is already given. Once you find the IP, then you can find the M. This is a simple question. First, for this, I need to find the responsivity R, which is equal to neta E lambda by HC. Neta is efficiency given as 0.8. E, I know 1.6 into 10 to the power minus 19. Lambda, it's given here 0.9 micrometers. By H and C. You know the value of H and C? So if you solve this part, you take your time to solve this part, then I will be giving the answer. So answer is 0.581 ampere watt inverse. This is the responsivity that you will be getting if you solve this part. Now, once you have got the responsivity, then you can calculate the photocurrent, which is I is equal to PR. So power, it is given in the question, input power, that is given as 0.5 microwatt, and R, which we have calculated here, 581, 0.581. If you solve this, you will get 0.291 microampere. Now, from here we can calculate the M multiplication factor. That will be I by IP, which is I is given in the question 11 microampere. IP we have calculated here 0.291. So the multiplication factor that we will be getting here is around 37.8. You can approximately say that 38. So that means that you will be getting 38 times more current as compared to pin photodiode. Now let's move to the next question. As you know that a pin photodiode produces n number of noises like short noise, thermal noise, dark current noise. So there are n number of noises that are generated in a pin photodiode or a APD photodiode. So in this question, we will be calculating the RMS value of the or mean square values of the different types of noises that are present in the pin photodiodes. So the question is like this: in gas, pin photodiode has the flowing parameter at a wavelength of 1300 nanometer. The ID is dark current is this much, and efficiency is 0.9. RL load resistor 100. For the incident optical power of 300 nanometers, 300 nanowatt. The temperature is 293 Kelvin and the received bandwidth is 200 megahertz. So first you need to find out the primary photocurrent. Second, the mean square short noise current. Third, the mean square dark current noise. And fourth, the mean square thermal noise current. These are the certain type of noises and primary photocurrent that we need to calculate here. You can solve along with me. First, I need to calculate the photocurrent. So the photocurrent, we know the formula, R into P, which is N Q lambda HC. If you put the value of everything, let's put neta given here 0.9, Q 1.6 into 10 to the power minus 19, lambda 1.3 into 10 to the power minus 6, and P input is 3 into 10 to the power minus 7. This upon HC 6.626 into 10 to the power minus 34, 3 into 10 to the power 8. Take your time to solve this part. So if you solve this part, the photocurrent that you will be getting in here is 0.282 microampere. This is the primary photocurrent that will be generated by the pin photodiode. This is the A part of the question. Let's move to the second part, B part. The mean square short noise current. The short noise current, the short noise are generated due to the random generation of the charge carriers. I square short is 2Q IP and B is the bandwidth. Put the value of all 2, Q is 1.6 into 10 to the power minus 19. IP is 0.282 into 10 to the power minus 6. And B bandwidth is 20 megahertz, which is 20 into 10 to the power 6. Solve this. I think you need to check your answer again. If you solve this, you will get something like 1.8 into 10 raised to power minus 18. And this is I short. If I find out the RMS value of this, I square short. So RMS value will be 1.34 nanoampere. So the RMS value is 1.34 nanoampere. Let me add a page here. Okay, let's move to the next part. Dark current. This will be 2Q ID into B 2 into 1.6 into 10 raised to power minus 19 into ID that is given in the question as 4 into 10 raised to power minus 9 and B 20 into 10 raised to power 6. To solve this, you will be getting here 2.56 into 10 raised to power minus 20 ampere square. And if I find the RMS value of this, it will be around 0.16 nanoampere. So here you can see one thing. The dark current is the noise due to dark current is negligible as compared to the noise due to the short noise. See, the short noise is 1.34 nanoampere, and the dark current, the noise due to the dark current is 0.16 nanoampere. Let's move to the next part, that is thermal noise. TH square, which is 4K. K is Boltzmann constant. TB upon RL. If you put the value of everything, 4K is 1.38 into 10 raised to power minus 23. T is 293 given in the question, and B is again given in the question 20 megahertz, 10 raised to power 6. RL, so it is given in the question as 1000 ohm. If you you can try it out yourself to solve this part. So ITH will be getting as 323 into 10 raised to power minus 18 ampere square. If I calculate the RMS value of this, it will be around 18 nanoampere. So these were the four parts that you need to calculate in this. Thermal current, dark current, short noise, thermal current noise, and dark current noise, and short mean square short noise current. So these are the values that we have got. All are in nanoampere, whereas the signal power was in microampere. So let's move to the next part of this question. In this next part, using the data that we have got in the above problem, you need to calculate the SNR, signal to noise ratio, using the data that we have got in the above part. So we know that what is signal to noise power. Obviously, it will be the ratio of signal power by noise power. The formula is already derived in the class, so I am directly writing the formula. IP square 2Q IP BE plus four KT B by RL. One thing you can see here that I am here neglecting the noise current that is produced by the dark current. Neglecting because that was very small as compared to the noise current that is produced by the short noise. So here I am neglecting the part, neglecting the mean square power of dark current, neglecting dark current noise because it was very small as compared to the other noises that were produced. If the value of the dark current noise was much higher as compared to the short noise, then we can neglect the short noise. So depending upon the values, I have neglected the dark current noise. So let's put the value of everything. So IP square that we have calculated in the previous part was 0.282 into 10 raised to power minus 6. This is whole square divided by 1.86 into this. We have calculated the short noises 1.86 into 10 raised to power minus 18. I'm just putting the value that we have calculated in the previous questions. This was 323 into 10 raised to power minus 18. To solve this, to solve it, I am giving some time for you to solve this part. solve this, we will get the answer as 245. So here it is written that SNR in decibel. So to convert it in decibel, we know that we need to take 10 log base 10 into 245. So here we will get the answer as 23.9 dB. So this is the answer for the questions. Now let's move to the next question. This question is basically related to the APD part. Just a minute. Yeah, this question is related to the APD part, avalanche photodiode. So here you need to calculate the SNR due to pin photodiode and due to the avalanche photodiode, and you need to compare both of this part. So let's read out the question first. Consider a silicon APD operating at a temperature of 300 Kelvin and with a load resistor of 100 ohm. For this APD, assume that the responsibility is 0.65 and let x equal to 0.3. The value of x depends upon the material. If it is a semiconductor, it is 0.3. If it is a germanium, it is 1. Those depend upon the material. If the dark current is neglected and 100 nanowatt of optical power falls on the photodetector, what is the optimum avalanche gain? So, and second thing, what is the SNR if the bandwidth is 100 megahertz? Third, what does the SNR of this APD compare with the corresponding SNR of a silicon pin photodiode? So if you see the formula of the SNR, first let me write the formula of the SNR. This is I square. M is the multiplication factor. This is the multiplication factor of the avalanche photodiode, which is produced due to the avalanche effect of the photodiodes. So our aim is to increase the SNR. What is our aim here? The aim is to increase the SNR. So if you want to increase the SNR, then what do you need to do? Can anyone tell me, do we need to increase the M or decrease the M? If M increases, SNR will increase or decrease? See, it depends. If M increases, then the numerator part will increase. But if M is increasing, then the denominator part is also increasing. That means there will be an optimum value for which the M should be kept at an optimum value. If you increase beyond that M, then the value of SNR may decrease. So there will be an optimum value of M. You see like graph between S and M will be somewhere like this, like optimum value of M. For this one particular M optimum, the SNR will be maximum, and for other value of M, the SNR will not be maximum. So to find the optimum value of M, can anyone tell me the approach how to find the optimum value of M? M optimum. See, to find the optimum value of M, this is a simple thing which we are doing since 11 and 12. Just differentiate this part and equate it to 0. Differentiating this part and equating it to 0, you will get the value of M. That will be the M optimum. So the formula that you will be getting after differentiating and equating it to 0, so the M value of M you will be getting here is 4K. Yeah, Gitansh have written the correct answer only. 4K T divided by X Q RL by IP whole raised to power 1 by X by 2. Here I am neglecting the dark current. If dark current is there, then IP plus ID will be there. Now you can put the value of X, T, Q and everything and find the value of M optimum. So let's put the value of. So Gitansh, you have forgotten the power part, I think. 4 K is 1.38 into 10 raised to power minus 23. T is 300 Kelvin given in the question. Divided by 0.3. Q is 1.6 into 10 raised to power minus 19. RL, it is again given in the question as 1000. And IP is 0.65 into 100 raised to power minus 9. IP is R into P. So R is 0.65 and P is 100 nanowatt. So basically in place of IP, I have written IP is R into P. So here R into P. Solve this part along with me. Solve it. Once you get the answer, you can write it here. In your final exam also, there may be some objective type question and there may be some numerical type of question. It will be a mix of both the questions in your final exams. So make the preparation as per the exams and make preparation of both the numerical type questions and the objective type questions. So here we'll be getting M opt equal to 42. It will be around 42. Now let's move to the next part and calculate the SNR. So we have calculated the M opt here. Now we need to calculate the SNR. Here we are neglecting the dark current. So first write the formula of the SNR. SNR is P square 2Q to Q. It's like 1.6 into 10 to minus 19, that is Q, into IP M raised to power 2.3 plus 4 KT upon RL BE. Let's put the value of everything. 0.65 into 100 for minus 9 into 42 someone has put, please put your mic off. 2Q IP. IP again I am writing here as R into P. Into 42 raised to power M raised to power 2.3 plus 4 KTB 4 K 1.38 into 10 raised to power minus 23 4K T is 300 RL is 1000 and this is whole B. B is 100 megahertz, 100 into 10 to the power 6. To solve this, you solve it by yourself. I will give you an answer once you solve it. So the answer, if you have calculated it, you can get it as 659. So the SNR will be 659. If you would find it in a dV scale, this will be around 28.2 dB. So this is the answer that you will be getting. Find the SNR of this. Now, in the last part, we need to calculate the SNR of the pin photodiode. If it is a pin photodiode, we need to calculate the SNR and compare with the result or compare with the SNR of the APT. So can anyone tell me how to find the SNR for the pin? So if this is SNR for the APT, so how to find the SNR for pin? The simple way to find the SNR for the pin is you put the value of M as 1. Put value of M as 1 because the multiplication factor is not there in photodiode. So in place of M, if you put M equal to 1, then the SNR that will come for pin photodiode. In the same formula, rest all the value will be same. Only the value that will change will be M. M will be 1. In place of 42, M will be 1. So if you find the value of SNR for M equal to 1, the value will come as 2.3. Or if you find it in a dV scale, it will be around 3.5 dB. So here you can see that here we have got 28.2 dB and here we are getting 3.5 dB. So the difference between 28.2 and 3.5 is around 24.7 dB. So the improved APT improves SNR by, in our question, 24.7 dB. So can anyone tell me, although it's improving the SNR, it's in terms, if we talk about in terms of SNR, then it is very good. But still, APT have a major disadvantage as compared to pin photodiode. So what is the disadvantage that APT is having as compared to pin photodiode? Noise, yeah, that is the correct answer. See, although it's increasing the SNR, but at the same time, what APD is doing, this is what? This is short noise. So APD is increasing the value of short noise and dark noise. So one way it is increasing the SNR, that is a good thing for any receiver, but at the same time it is increasing the noise, short noise and the dark noise. So this is increased by the APT. So this is the disadvantage of the APT. So depending upon your application, you can use the APD or SNR or pin photodiode. So that's it for the question part of view. This is it from my side today. And one more thing, when you will be seeing that questions in your assignment type, there are certain questions in assignment related to MIMO and all that. Right? So that all question you need to answer by yourself. You need to think analytically that how this question will be answered. See, suppose here we have a transmitter and here we have a receiver. Now this receiver will have a field of view like this. If the signal comes from this side, then it will not receive. This is the field of view. If the signal come in this field of view, then only it can receive the signal. So the notation you need to take care for your assignment part. This is denoted by phi, incidence angle. Sorry, this is the incidence angle. This is denoted by theta. And this field of view angle is denoted by sides C. So if the field of view is larger, then it can capture more amount of signal, but at the same time, it can capture more amount of noise also. The larger field of view has advantage as well as disadvantage also. Disadvantage in terms of that it may capture more amount of noise and more amount of multipath signals. This is the line of sight signal, and if we talk about non-line of sight signal, then the signal may come like this also. This is non-line of sight signal. 1, 2. After 3 reflection, you are getting the signal. The signal may be line of sight, signal may be non-line of sight. The signal that is you are getting line of sight, and that signal you are getting with non-line of sight, there will be a time difference between these two signals. And based on this, there is also some calculation, spread delay. So how this spread delay is affecting the bit rate and bandwidth, or bandwidth, how much spread delay is allowed in your signal. As the field of view will be narrower, the spread delay will be small because less number of reflected signal will come. This reflected signal only causing a time delay. Due to this time delay, there is a spread delay. So if our signal have a pulse width like this t, so the spread delay in generally should be, if I tell the spread delay by tau, this should be 10 times, tau should be like 10 times of t, or smaller than that. Tau should be smaller than 10 times of t. So these all these things are being taught in the class. So some of the questions are from this part only. So that you have to think analytically how these systems will behave if there be a multiple transmitter and multiple receiver. So all this you need to think like TX1, TX2. What is the importance of narrower field of view? What is the importance of a wider field of view? So these all things you need to think analytically and need to answer in the questions that have been asked in the assignment part. You know? I think I have made my point clear here. So here we will stop here. We will end our session here. Do anyone have any doubt? Then can ask me.
Hello.
Yeah, Vipul.
Sir, can provide any study material related to this training?
So study material is already given by sir. There are 3 references books that is already written in that that if you see the course section, na, there are 3 books are written. I think one is from Cambridge and one is
Is there any soft copy available or not?
yeah. You if you find it, soft copy is available in the Google.
Okay.
You surely find it. I have searched in the Google. Soft copy is there for all the books that is written in that. One is Gerd Kieser, Gerd Kieser.
Yes, God Kaiser available, but about 5G, ये 5G वाला सेक्शन जो है ना वो थोड़ा
Okay, okay. What you do? You mail me, है ना? So
Yes.
you mail me. Do you have my mail ID?
No, sir. Please text message in this section, message section, please.
Just a minute. Just a minute. See, my mail ID is
Okay.
lalani dot one at the rate of iitj.ac.in.
Thank you, sir. I will mail.
You mail me regarding the books on whatever you require. So I will send you. Na?
Okay. Thank you.
Okay. Thank you.
Sir, regarding the same assignment,
Yeah, I have seen that some of the questions were.
actually the problem is that we are doing it for the credit transfer course, and for acquiring a certificate, there is certain criteria that the average score in the assignments must be like minimum 10. So we need to maintain that score, and if we are not able to do these assignments, and if the problem is coming due to
Yeah,
because
Gitansh,
of
your voice
mismatch
is.
in the
Hello.
Yeah,
Yes,
Gitansh,
sir.
there
I
was some
was
network issue.
telling that
Yeah.
to get for us to get a certificate, there was a certain criteria that we must score at least 10 marks in the average assignments, in the best of 8 average assignments. So if this is the situation, like assignment questions are not based on what that is being taught, then it's we are to disadvantage.
Yeah,
So can
yeah.
you please convey
That's
it to the course coordinator or anyone who's above so that they can take a look and
okay. Actually, course and converter is Anand Srivastava sir. So I do not have much of communication with Anand Srivastava sir. I generally I have a communication with the NPTEL team, and so directly I don't have any communication with Anand Srivastava sir. So I can convey it to the team of NPTEL. You can also convey it the mail that you are receiving. So you can also directly convey it that the questions are not exactly. But what I have seen that uh, there are some analytical questions. If you think analytically, you can get the answer. And the few questions only, three or four questions are only out of that is okay. Remaining all the questions are questions can be answered. Or even week 1 and week 2 questions were like directly and straightforward. This
yes, sir.
time,
Week 1 and week 2 were I was able to do week 1 and week 2 questions. Also in week 3, 1 to 5 questions I was able to attempt, but from 5 to 10 I was not able. And then if when I proceeded to week 4, then I saw that week 4 questions are there are more questions in week 4 assignment that are unrelated to the week 4's content. So it keeps on increasing this phenomena there. So you can have a look yourself also, and you
yeah,
can see that.
I have a look on week 3 part. Week 4 part I didn't look at, but yeah, I know there are certain 3 or 4 questions that were somewhere out of scopes, and you need to think analytically and answer the question as much as you can. That what I can say. I will try to convey this message to the team and NPTEL team. Huh?
Okay, okay, sir. Thank you, sir.
Okay, thank you very much.